for introduction. So I'm Makoto Hirota from Tohoku University in the Institute of Fluid Science. So today I'd like to talk about this topic, and as you can see, so this topic is quite related to the previous talk given by Professor Furukawa. So I think the introduction is quite similar. So, but anyway, so I'd like to first introduce the magnetohydrodynamic relaxation phenomena. So when talk about magnetohydrodynamic or MHD relaxation, so magnetic helicity is the important physical quantity. So this is naively defined by the inner product between vector magnetic field, vector field, and vector potential A. Inner product integrated over the domain. So this is so-called magnetic helicity. And as already introduced by Professor Furukawa, this is constant of motion in the ideal plasma. So ideal means there is no dissipation term in the equations. So if we consider MHD as a Hamiltonian system, so this is the so-called Casimir invariance. And physically or topologically, this quantity is so-called the measure of the extent to which the field line wrap and coil around one another. So this is a generalized concept of linking number in a topology. So, but this linking number is defined for the smooth vector field. So this is not the integer. So this is the real number actually. And there is a very famous theory given by Bolger and Taylor. So they first assume, as a conjecture, they assume that this property of magnetohydrodynamics. So if you consider magnetically confined plasmas, so it tends to relax to the minimum energy state while conserving the total helicity. So if you consider these two invariants, the energy decreases faster than the magnetic helicity. So this is just a tendency or assumption. But based on this conjecture, so you can minimize energy while conserving the magnetic helicity. So this is variational problem. So if you solve this variational problem, you will get this equation as the Euler-Lagrange equation. And this means that the relaxed state is the basically eigenfunction of this Carl operator. The lambda is eigenvalue. And this is also known as a force-free field because the curl B is the current J. So J cross B equals 0 because of this property. So which means that the Lorentz force is 0 everywhere. So that's why this is called force-free. And this is very important in the various phenomena. So for example, if you consider the solar flare, so we typically observe this kind of magnetic field structure called corona loop. And this structure is well approximated by this force-free field. So this is a numerical result given by Professor Kusano. So in this way, the relaxed state is actually observed in the nature. And of course, this relaxation theory is important for magnetic confinement of plasma. So this relaxed state can be desirable for plasma confinement for the purpose of nuclear fusion reactor. And as you can imagine, so this relaxed state usually stable to the perturbation. And this confinement type is called reversed field pinch. And so again, this is the experimental device which tries to confine the high temperature plasma in the torus geometry. And the reversed field pinch is schematically shown like this. So because of the relaxation, the magnetic field relaxed to such a helical or twisted structure like this. But however, so if you consider the resistive MHD, so magnetic helicity also decays more or less. So in order to maintain this relaxed state or control this relaxed state, we have to keep supplying magnetic helicity externally. And there are several methods to inject magnetic helicity to plasma. So, but today I'd like to talk about this AC magnetic helicity injection, or which is also known as oscillating field current drive. And in this method, we need at least 2 AC voltages. We need to apply 2 AC voltage to the plasmas, and these 2 AC voltage are suitably phased to inject magnetic helicity into plasma. So this is periodic magnetic helicity injection, but this, because of this injected helicity, we can expect the Taylor relaxation, and as the relaxed state, we will observe the DC current. However, this is already experimentally observed, but theoretically there are many difficulties. So first, this very famous theory, Bolger-Taylor's relaxation theory, is based on the conjecture, as I explained. So this is just assumption. And if you look at the detailed relaxation process, so this involves so-called magnetic reconnection and dynamo effect. And this is very complicated nonlinear process. So, and this is formally called turbulent transport, but there is no established theory which explains this turbulent transport. So it is difficult to predict and control this relaxed state. And there are many questions about the prediction of relaxed state. So the goal of this work is to clarify the detailed physics of this nonlinear relaxation process, followed by magnetic helicity injection by using the direct numerical simulation. And to understand the physics, so I consider very simple geometry. And again, so we consider cylindrical plasma, and which is periodic in the z direction. And in this geometry, we can apply 2 voltage along the theta and z direction. And this is the definition of loop voltage along z and theta. And in this geometry, the magnetic helicity is defined like this, because this geometry is multiply connected. So we have another term here. And the time derivative of magnetic helicity is given like this. And there are 2 terms. So one is the dissipation due to the resistivity. The other is the injection rate. So this injection term is related to the voltage applied on the boundary. So by choosing this voltage, we can inject magnetic helicity into the plasmas. So in this case, we are considering the AC magnetic helicity injection. So this psi z and psi theta are represented by cosine function like this. So we can inject magnetic helicity on cycle average like this. And the governing equation is the standard MHD equation. But in order to apply the voltage at the boundary, we have to use the vector potential A instead of the magnetic field. So this is the evolution equation for A. And physically, this is called Ohm's law. And another is the equation of motion, including the electromagnetic force. And here, I used the Coulomb gauge for the vector potential. And this is the boundary condition for these 2 equations. And as for velocity, I imposed the no-slip boundary condition. But as for vector potential, I applied the AC voltage like this. This is time-dependent Dirichlet boundary condition. And as for pressure term, I used the 2 cases, 2 extreme cases. So one is an incompressible model, so divergence V equals 0. In this case, we have to solve Poisson equation for pressure. And the other is the 0 pressure model. So this is quite similar to the 0 beta model introduced by Prof. Furukawa. So pressure is just neglected. And as a preliminary theory, we can expect what happens when we apply AC voltage. So first, we can obtain this exact solution, which represents so-called skin effect. So because we are applying AC voltage at the boundary, first magnetic diffusion occurs near the boundary. So this is the analytic solution. And the width of this layer is called resistive skin depth, defined like this. This is classical effect. But because this is the exact solution, so in order to trigger the relaxation, so this solution must be unstable to some instabilities. So this is the first step. And here, so I introduced Fourier decomposition in the theta and z direction. So this solution is 0, 0 means axis symmetric solution. And next preliminary theory is again Taylor relaxation theory. So as I said in the introduction, so this is the so-called force-free equilibrium state or minimum energy state. And lambda is the eigenvalue. So actually the minimum eigenvalue corresponds to the minimum energy state. And in the cylindrical geometry, we can solve this equation analytically. And the one candidate for minimum energy state is the axis symmetric solution. So m and wave number for z is equal to 0. And this is the solution given by the Resistive function J1 and J0. This is the analytic solution. But in some cases, there is another candidate for minimum energy state. This is called helical Taylor state. And this solution has the mode number 1 in the theta direction. So this is so-called helical structure. And the solution is given like this. And in general, we can expect the minimum energy state is the mixture of these two solutions. This is the Taylor theory. And now I want to introduce or give you the result of our numerical simulation. And as a typical case, I choose these parameters. But essentially, in this picture, I use the incompressible model. And this is the important inequality. So first, so-called Alfvén time, this is the typical time of wave period, is set to be the 2 pi, order 1. And in this case, you have to apply the AC voltage with the period, which must be much longer than the Alfvén time. And the resistive decay time should be much more larger than this AC period. Under this condition or inequality, we can inject magnetic helicity. And this is the actual time evolution given by our simulation. So this is the t equals 0, and as time goes, the magnetic helicity increases like this. But finally, this will be saturated at a certain level. And at the same time, the actual current Iz is oscillating, but we can observe that on average, on cycle average, we can obtain the DC current in this way. So this DC current is the evidence of the appearance of a relaxed state. And this movie shows just only one cycle of magnetic helicity injection at the saturated phase. So in this study, we find that the existence of actual magnetic field is very important. So we can apply uniform magnetic field in the z direction as the parameter. So if there is a certain magnetic field at 0.4, we can observe the axis symmetric relaxed state. So in this case, the current, DC current, is directed in the z direction. But for weak magnetic field, Pz equals 0, we observe another type of relaxed states, which is correspond to the helical Taylor state. So in this case, because of the plus and minus positive and negative current, so total DC current is 0, but actually we can observe this helical structure in the core region. So this is the magnetic energy spectrum. So with the guide field Bz, as we already observed, the axisymmetric component, Fourier component, is the dominant, always dominant, like this. But without guide field Bz, the m equal 1, n equal 1 Fourier mode is dominant always. So you can actually obtain the helical state on time average. And this is the cycle average profile of the dominant Fourier component. So in the right-hand side, so I plotted the only axisymmetric Fourier component, 0, 0 component. And this steep structure corresponds to the resistive spin layer. But in the core region, we can observe smooth profile of magnetic field and current. And this indeed corresponds to the Bessel function predicted by the theory. And this is for helical case, and I'm showing the m equal 1, n equal 1 component. And this also agrees with the Taylor relaxed state. And so this movie shows another approach to the identification of Taylor state. So in the Taylor state, the current must be equal to lambda times magnetic field. So current must be proportional to the magnetic field. So I checked this condition numerically. So if we consider this quantity, J dot B divided by B square, this must be constant lambda. So and on the other hand, so if we calculate J cross B, this must be 0 if Taylor state is generated. So this is the radial profile of this quantity. And if you look at J dot B, the red one, so this is very noisy, but we can actually observe spatially uniform profile of lambda. Yeah, and in this case, lambda is about 3, and in this case, lambda is about 1.6. I calculated numerically. But still, we can observe some resistive layer at near the boundary. And so finally, I want to make some theoretical prediction about the magnitude of this Taylor relaxed state. So as a theoretical model, I considered Helicity balance, which means the Helicity injection versus Helicity dissipation. So clearly we inject magnetic Helicity at the boundary. So we already know the Helicity injection rate on the time average. This, and however, not all of this injected Helicity is absorbed into the Taylor state. So because of the existence of resistive skin layer and many so-called magnetic reconnection process, so there are many mechanisms which dissipate the magnetic Helicity. But however, it is very difficult to estimate the dissipation rate due to these complicated turbulent transport. So, but however, we can analytically calculate the dissipation rate of Taylor state like this. So by substituting the solution for Taylor state, we can estimate the decay rate of Taylor state. This. So as the simplest Helicity balance, I simply neglected this unknown Helicity dissipation rate and just consider the balance of given injection rate and the dissipation rate of Taylor relaxation. And this simplified helicity balance give you rather large magnitude of saturation level like this. But I think this is theoretically the first step to predict how much the Taylor relaxation, how much Taylor state is generated. And this is a comparison between the Taylor state and theoretical estimate and the numerical result. And the red curve are given by the theoretical helicity balance. And you can see there are many good agreement with the theory and the numerical simulation. But however, first, if the guide field Pz is greater than 1, we can find that the relaxation to the core becomes inefficient. So if Bz is greater than 1, so this lambda and DC current and helicity goes to 0, and which is far from the theoretical estimated value. So which means that there's no relaxation. No relaxation occurs with such a strong guide field. But if the guide field is less than 1, we can observe some relaxation process, and only in this case, there's good agreement between theory and simulation. And also appearance of helical component is expected theoretically, and theoretically it is expected when Bz equals 0.17. And there are some difference between theory and simulation, but indeed we can observe we can predict the appearance of a helical Taylor state. And this is a summary of our work. So first, we developed a numerical code that solves the resistive MHD equation. But here, you have to solve the vector potential A instead of magnetic field. And we confirmed the Taylor relaxed state only in the core region. The H region is dominated by the resistive skin layer. And only when the guide field is less than 1, we observe the efficient relaxation process. And if Bz is less than 0.2, we also observe helically symmetric relaxed state. And we already made some theoretical prediction about the magnitude of relaxed state. So I think that's all. So thank you for your attention.